Okay, now angular momentum carries energy. So I've said that before. So the carrier is L, and there is a strength which tells us how much energy the angular momentum carries, and that is omega. And we can put these L and omega together to find out how much energy is carried by the following equation. U, which is the equation with the symbol for energy, is equal to 1/2 times the angular momentum times the rotation speed. So if I know the angular momentum of something and I know the rotation speed, then I can find out what the energy is. So we can apply this to the example where you had where you had the plates spinning. Before, you had a high value of omega. It was 12.5 per second, I think. And so then U would be equal to 1/2 times L, the angular momentum, times omega before. Now after, we said that the same amount of angular momentum was shared by both of those plates, but they were rotating at a lower speed. So we had a low omega. I think it was about 6 per second. And the energy after would be 1/2 times L. It was the same L afterwards as it was before. It just was shared by the two different plates rather than being all in one plate. So this L must be the same as that one. But the difference is that the rotation speed after here is smaller than it was before. So this is after. Well, if the rotation speed after is less than the rotation speed before, then it must be that the energy before, the energy in the bottom plate must be greater than the energy afterwards, which is shared by both plates. Where does the extra energy go? We know that if before the plate is dropped, the second plate is dropped, there's more energy contained by both plates than there is after in the rotation. What happens to the extra energy? Energy can't be destroyed. It has to do something. Well, when we draw an energy diagram, it looks a little bit like this. Here's angular momentum carrying the energy. So beforehand, you have a high amount of angular momentum. And now vertical on this diagram will be higher angular momentum. So we start with angular momentum with a high amount of a high rotation speed, and it carries in some energy. Then there's a collision between the plates, and that angular momentum gets transferred to the other plate. Part of it gets transferred to the other plate, and all that angular momentum is still in the two plates, but now the angular momentum is the rotation speed is lower than it was before. We had the same amount of angular momentum, but rotation speed is lower. So this would be omega after, and this would be omega before. Now, in this angular momentum, the angular momentum of both plates rotating together, also carries energy, but it carries less energy. Right? So this would be the energy after, and this here would be the energy before. As I said here, the energy before here is greater than the energy after. Well, if you have put in all this energy, and then you're only getting out less energy, then where does the extra energy go? Energy can't be destroyed, it's got to go somewhere. Well, it turns out that the difference, the extra energy that goes in here, which didn't get carried off at the end, which wasn't still in the rotating plates, gets carried off by our favorite carrier, entropy. Entropy is created when those two plates rub together. Maybe that's not surprising. If you take those two plates and you rub them together, one against the other one, there'll be friction between them, and that will heat them up. So when you have angular momentum going from a high rotation speed to a low rotation speed, then you create entropy in the process. Let me give you another example of that.